So, good morning, everyone. Today we'll be discussing about variational quantum eigensolver. So, let me quickly share my screen and we can start the session. So, in today's class, we will be discussing about variational quantum eigensolver, which is kind of an algorithm to find the ground state energies of molecules. So, variational quantum eigensolver is particularly used in solving chemistry-based problems. For example, finding the ground state of a hydrogen molecule. Like in our 10th class chemistry textbooks, they directly gave that the ground state of it or the bond length between two hydrogen atoms is for example x. So how do we know that it's x? Like we are not sure. Like we they just gave the number, and like we are taking that considering the fact that who wrote that are professionals in the field or who are scientists and who discovered that. So by using the help of variational quantum eigensolver, what we can do is like we can find the ground state energy of different molecules, different proteins, and also we can find the bond length. It's basically used for solving chemistry based problems. Okay, so let us go ahead. So the outline of today's lecture is, first we'll be discussing about quantum algorithms, and then let us start with the basics of electronic structure problem, like what is electronic structure problem, and like why, that is the basic, that is how variational quantum solvers start. So we will first discuss about electronic structure problem. So variational eigensolver basically, like find solution to this electronic structure problem. So we will see that in the coming slides, and then we will see how electronic structure problem can be, like can be computed on quantum computers. It's like all the data from electronic structure problem will be chemistry or will be mathematics, like, but we need to map that onto quantum computers. So we will also see how we are going to map that onto qubits and all of that, and then sorry, and then we'll see, like how, as I said, like how we map the Hamiltonians, like how we'll find the eigenvalues, and the pros and cons of VQE and the challenges of VQE. Like there are a lot of hardware challenges implementing variational quantum eigensolver. It's not like variational quantum eigensolver can be used for like less number of atoms molecule, like for example hydrogen, lithium, such kind of molecules. But for example, if you take the like higher metals, or like higher atoms, which has more number of electrons, protons, and all of that, then variational quantum eigensolver can faces issues with that. Like we'll see what are all the challenges, like noise and all of that. So let us move ahead. So yeah, so what are quantum algorithms? So quantum algorithms are particularly designed, the algorithms that are particularly designed to run on quantum computers, right? Like so why the name quantum algorithms. So classical algorithms are particularly designed to run on classical computers. So quantum algorithms are of again divided into two types. So fully quantum algorithms and hybrid quantum classical algorithms. So, quantum algorithms take the advantage of quantum effects such as superposition and entanglement, and then they produce the result, and then then they compute on quantum computers, and then they produce the result. So, why do we use quantum algorithm? Because they are efficient, and they are a lot more faster in computing the result than any classical algorithm. And sometimes classical algorithm fail to run a lot of some big problems like NP hard problems. Classical algorithms, they perform poor for a particular set of problems. So we can use quantum algorithms for such particular set of problems, and then we can use quantum algorithms and bring out the results where classical algorithms fail. Okay, so what are fully quantum algorithms? Fully quantum algorithms are particularly the algorithms that only run on a quantum computer. Like you don't need a classical computer to like to run the fully quantum algorithms. Like you just need a you can run the whole algorithm on a quantum computer. Okay, so for example, quantum algorithms can be Shor's algorithm, HHL algorithm. So Shor's algorithm can be used for prime factorization. For example, there is a number and you need to find, for example, let us take that let us take a number to be, like some random number. For example, the number is 21. Okay, so you need to find two prime numbers. When you multiply those two prime numbers, you will get 21. Okay, so what are the two prime numbers? 7 and 3. 7 3 is 21, right? So we can find the prime factors of a particular number using Shor's algorithm. 21 is very small number, like it will not take a lot of qubits, but when you take a bigger prime number, and when you want to find two prime numbers of that particular, when you multiply two prime numbers, then you want to get a particular number, then we use Shor's algorithm. Okay, so HHL algorithm can be used in solving linear equations. Like in mathematics, we know that like solving linear equations is also a particular set of a problem. Further, there are different techniques to solve linear equations. So in quantum, when you come to quantum field, then we use HHL algorithm to solve linear equations. Okay, so then Gruer's algorithm. So Gruer's algorithm, so for example, there is a set of data and you need to find a particular, like for example, there is odd numbers and even numbers. Then you need to find a particular number which is odd, or for particular, like if you want to choose an odd one out from a particular data set, then we use Grover search algorithm. Grover search algorithm will be, like the class will be taken in the evening from 7 to 9, if I'm not wrong. And then quantum phase estimation. So quantum phase estimation is a, like VQE is particularly quantum phase estimation, but an extended version of quantum phase estimation. I hope quantum phase estimation is already taken by one of our volunteers. So why do we use quantum phase estimation? Quantum phase estimation is used to find the eigenvalues of a particular operator. Okay. So now let us come to hybrid quantum classical algorithms. So what is hybrid quantum classical algorithm? So hybrid quantum classical algorithms are like you use quantum computer as well as a classical computer to compute a particular algorithm. Okay, like you don't simply use a quantum algorithm as you use for fully quantum algorithms. So you need a quantum algorithm as well as a classical algorithm. Sorry, you need a quantum computer as well as a classical computer to run hybrid algorithms. For example, QAOA, quantum approximation and optimization algorithm, which is used to find the optimization problem, such as traveling salesman problem. So what it does is like it computes the problem on a quantum computer, and then it sends back the results to a classical computer, and then it optimizes. For example, the parameters will be optimized on a classical computer, and then it sends back to the quantum computer again. And then the optimized results, like for example, the parameters will be optimized, right? X, Y, Z will be optimized. So again, the quantum computer will use this optimized results and check the results. If it is the lowest value, then that will be the output. Okay, if it's not the lowest value, again the results will be sent to a classical computer, and then the loop goes on until and unless you find the lowest value of the particular problem, or until and unless you find the right value of the problem. So QAOA is used to find the optimization problems, and VQE is used to find the eigenvalues of a Hamiltonian. Like we will discuss that. Like to put it in layman terms, like it's used to find the ground states of a particular molecule. We can use. So let us discuss in detail about how hybrid quantum classical algorithms work in detail in the coming slides. So let us discuss about electronic structure problem, like a molecular and electronic Schrodinger equation. So, any chemistry problem can be represented in the form of electronic Schrodinger equation. Okay, so whatever you take, like because when you narrow it down to when you go to the uh, what like when you go deep down, when you go to the quantum mechanical perspective, so then every atom has some energy, right? Like there is some kinetic energy to an electron, kinetic energy to nucleon. Like there's electrostatic interaction between electrons and nucleons, through which electrons can revolve around the nucleus, right? Like only then, like only when the nucleus has some like some interaction between electrons and the nuclei, only then it can hold up those electrons revolving around the nuclei, and it can put those electrons in a particular orbit, right? Like electrons revolve around the nucleus. So when you narrow it down, like when you go deep down to the quantum mechanical perspective, then everything can be written as a molecular Hamiltonian. Like every compound or every molecule can be represented in the form of molecular Hamiltonian. So which makes our things simpler. Like so we have a standard set through which we can see a particular problem, we can say, like particular atom. So every molecule can be stated in the form of molecular Hamiltonian. So let us discuss, like what is what. So H is the Hamiltonian and psi is the wave function. In the form of R is both distances. R is small r is the distance and capital R is the distance. So E is the eigenvalues. Okay, so E is the eigenvalues, H is the Hamiltonian, and psi is the wave function. So we can represent the molecular Hamiltonian like this. So what are all of these? Like the first one is the kinetic energy of electrons. Second one is the kinetic energy of nucleus. Third one is the electrostatic interaction between electrons and nuclei. Fourth one is the electrostatic interactions between only electrons. And fifth one is electrostatic interaction between nuclei. Okay. So first we will describe the molecular Hamiltonian before solving a particular problem. For example, if you are solving a hydrogen, if you are thinking of finding the ground state energy of hydrogen, then first what we need to do is, like, we need to define the molecular Hamiltonian. Okay, so we can define it like this. Like for example, when you solve it by yourself in quantum computers, like you don't need to define molecular Hamiltonian by yourself. Like the molecular Hamiltonians are already defined for particular set of molecules. For example, H2, the molecular Hamiltonian is already there. You just need to like bring it down to your Google Colab or Google Notebook. So let's go further and see. Then there is Born-Oppenheimer approximation. So for example, so this is the molecular Hamiltonian H of a given particular molecule. Okay, so there are total 5 terms, and computing 5 terms on a quantum computer is, like, it will take a lot of qubits, and it is also computationally expensive. So what Born-Oppenheimer approximation says is, when mass of nuclei is greater than the mass of electron, then you don't need to consider the kinetic energy of electrons. So kinetic energy of electrons, you can ignore them. Okay, and also it says that electrons adjust instantaneously to the movements of nuclei. So which means that electrostatic interaction between electrons is constant. So when it is constant, when it is constant, you can ignore that. Okay, so what we do is, like, taking Born-Oppenheimer approximation in sorry, someone's joining the link, I guess. Hello, Ayan. Yeah, is there? Okay. Hello, Roshan. Is there anyone else who is joining, or, like, should I continue?
Not sure.
Acha, fine. So, like, I mean, we are already half. I mean, I discussed some introduction to VQE, so I will brief it for you, like what we have discussed so far. So what we have discussed is, like, I discussed about quantum algorithms and hybrid quantum classical algorithms. So fully quantum algorithms are used only on quantum computers. Okay, like only designed to use on quantum computers. Hybrid quantum classical algorithms are not like that. It requires quantum computers as well as classical computers. We need both of them to run a particular algorithm. So uh, such kind of algorithms are called as hybrid quantum classical algorithms, and QoA and VQE are two of such algorithms. So VQE is used to find eigenvalues of a Hamiltonian. To put it in layman terms, like, we can say that it's used to find the ground state energies, or ground state structure of a particular protein or particular molecule. And then we discussed why we need VQE. Like, VQE is used to, as I discussed now, VQE is used to find the eigenvalues of a Hamiltonian. So we can find the ground state energies of a particular molecule. For example, there is hydrogen molecule H2. We can find the ground state energy, like the lowest stable state energy, to put it like that. So we can find the stable state energy of hydrogen molecules using variational quantum eigensolver. So variational quantum eigensolver is particularly used for chemistry based problems. Okay, like to find the bond length, to find the bond angle, the distance between two molecules, ground state energy. Particularly, we are interested in ground state energy because because that is a stable state energy of a particular molecule. Like a molecule will usually be in that state, right? Like the ground state or the stable state. So when you give some more energy to it, then the electrons excite from one orbit to another orbit, and then the state of the molecule changes. So we are particularly interested in finding the ground state energy of the molecule of a particular, it may be protein or particular molecule. Okay? So after that we discussed the electronic structure, Schrodinger equation. So H is the Hamiltonian, psi is wave function, and E is eigenvalues. Okay, so any molecule can be written as the can be like put it down as a molecular Hamiltonian. For example, there is H2. You can take nitrogen atom like N2. Whatever you take, it can be written as a molecular in the form of molecular Hamiltonian. So what are all do you need to consider to write the molecular Hamiltonian? You need to consider the kinetic energy of electrons. You need to consider kinetic energy of nucleus. You need to consider electrostatic interaction between electrons and nuclei, and then you need to consider electrostatic interaction between electrons. You need to also consider electrostatic interaction between nuclei. So you need to consider all of these parameters while writing the molecular Hamiltonian of a particular molecule or a particular chemistry based compound. So to make our things simpler, Born-Oppenheimer approximation states that when mass of nuclei is greater than the mass of electron, you can ignore that, right? Like for example, usually in every like in every molecule or in every whatever molecule you take, usually the mass of nuclei is a lot greater than the mass of electron, right? Like that is how so why electrons revolve around the nucleus, like because the mass of nuclei is a lot more than the mass of electron. So electrons revolve around the nucleus. So we can ignore that term, right? Like so here there are total 5 terms. So we can ignore the first term because mass of nuclei is greater than the mass of electron by Born-Oppenheimer approximation. And it also states that electrons instantaneously adjust to the moments of nuclei, which means the electrostatic interaction between electrons is constant. So when it is constant, so you can ignore that too. So we will be left out with 3 terms in total while when we want to write the electronic Hamiltonian of a given molecule, right? Like for example, if you want to write the electronic Hamiltonian of a molecular Hamiltonian of a particular molecule, then you don't need to consider the kinetic energy of the electrons, and also you don't need to consider the electrostatic interaction between electrons. So you can only consider kinetic energy of nucleus, electrostatic interaction between electrons and nuclei, and then electrostatic interaction between nuclei. So to make our things simpler, like there are already defined molecular Hamiltonians. For example, if you want to find the ground state energy of a H2 molecule, then the molecular Hamiltonian is already defined for you. You don't need to, again find the kinetic energies of electrons and all of this. So molecular Hamiltonians are already predefined for us. We just need to, import them into our collab. So moving further, as I discussed now, so we will be left out with three terms, right? So we will be left out with 3 terms. So what is our main agenda is to find the eigenvalue of the. Seems like someone else is joining. Yeah. So the main agenda of the video is to find the eigenvalue of this particular problem. So we have 3 terms, so we need to find the eigenvalue. So which is E. So why do we need eigenvalues of a particular problem? Because we can using the eigenvalues we can describe the nuclear motion of the for example how the electrons are revolving around the nucleus. We can describe about that. So we will get to know how a nuclear motion of the molecule, like of the electrons. And we can, for example, if we use classical algorithms to solve this, it is not exactly solved. For example, there is some error between the real value and the predicted value or the computed value. For example, if you take hydrogen, even for hydrogen itself, it takes a lot of time and the answer is not exactly there. So why we use quantum hybrid algorithms or hybrid quantum classical algorithms to find the eigenvalues of this particular set of problem. So using classical computers, we are only getting approximate solution. So we can use quantum algorithms like variational quantum eigensolver to find the eigenvalues or to find the a solution to the electronic Hamiltonian. Okay. So as I discussed before, so this is how VQE works. Okay, so I mean, this is not exactly how VQE works. This is only the quantum part of VQE, how VQE works. Like there is also classical version, like all these measurements, as you can see, the green color arrow goes to the measurement, right? Like it will measure, and then the values are being sent to the classical computer, and then it will optimize the parameters, and then it will again send to the quantum computer. Okay, and then it will again compute the result. It will measure the output, and if it is the lowest output, if it is the lowest ground state energy that you can ever get, then that will be the output of our that will be the output of our um, that will be the output of our problem, right? Like what we need to find is the stable state energy or the ground state energy of the molecule. So ground state energy is the least energy that a particular molecule can be in, right? Like that is the stable state energy a particular molecule can be in, is the least energy that a molecule can attain. So what we do is like we find for the lowest value, and then if that is the lowest value, then that will be the answer. If it is not the lowest value, then the measurement goes to the it goes to the classical computer. The classical computer optimizes the parameters, and it will again send to the quantum computer, and the loop goes on until and unless you find the lowest energy state of a particular molecule or the particular problem, whatever you are interested in, right? So the quantum system, this is the molecule that we use, and then we map that into the quantum computer, and then again we like after you map the quantum systems to the quantum computer, or you map the Hamiltonian to the qubits, and then you measure you measure it, you get the results, and then you send it back to the classical computer, and the loop goes on until and unless you find the lowest energy. So, so there are two types of quantum computers: analog quantum computers and digital quantum computers. So let us discuss in detail, like what analog quantum computers and what are digital quantum computers. So in analog quantum computers, we study the parameters, like we tune the particular parameters. Okay, like for example, as I discussed, now the parameters are being optimized by the classical computer. So we study how the parameters are getting tuned, or we also study the how classical computers are also working, like because they are the ones which optimizes the parameters for us, right? So in analog quantum computing, we studied that how the parameters are being tuned. In digital quantum computing, we are only interested in like finding the eigenvalues of the given Hamiltonian. Like anyway, the classical computers are doing the work for us, but we are not interested in what classical computers are doing for us. Like we are only interested in the quantum part, like how we are only interested in finding the eigenvalues of the given Hamiltonian. Okay, so in analog quantum computing, we map the Hamiltonian onto the simulator, like it's like we map the Hamiltonian to a particular set of qubits, or we get a gates, and then the gates are being because quantum computers can only understand the language of quantum computers is qubits, right? Like you need to map the Hamiltonian to a particular qubits, like you need to map them. So there are different techniques to map qubits to map Hamiltonians onto the quantum systems. So analog quantum computers does that. In digital quantum computing, Hamiltonian is decomposed into a set of elementary quantum gates, which is basically the same. Here you map that by yourself using a particular process, but in digital quantum computer, like the Hamiltonian can be like using a like using a decompose technique. Then you can directly decompose the Hamiltonian to a particular set of quantum gates, and then you can like once you have the quantum gates, you can directly use them to run it on the quantum computer. So that is the main difference between analog quantum computing and digital quantum computing. So next, let us as I discussed before, so quantum phase estimation is basically the extended version. VQE is basically the extended version of quantum phase estimation, and quantum phase estimation is I hope it's already covered by one of our volunteers, right? So what we do in quantum phase estimation is like we'll have a unitary operator. Let us take it as ei5, and then we approximate the we what we does is like we find the approximate eigenstate of that particular unitary operator using quantum computer and using quantum phase estimation. The output will be binary representation of the phi, right? Like the output will be the binary representation of phi. So why are we using this? Like it is proven that there is experimental speed up for finding eigenvalues and eigenvectors using quantum phase estimation. Like you can also use other extended versions. Like why are we only particularly using quantum phase estimation as an extended version of variational quantum eigensolver? Because it has been proven that it showed experimental speed up in finding the eigenvalues and eigenvectors of particular molecule. So as you can see, this is basically the like whole VQE is basically like a QPE plus some other quantum circuit, right? Like so QPE is already integrated in a VQE. So why like it's called as the extended version. So VQE is the extended version of quantum phase estimation. So once we use this ancilla qubits, it is found that the accuracy of the particular problem increased. So there are other parameters, like once you use the more the number of repetitions, the more the accuracy and the more the precision, right? Like for example, you only repeated the algorithm twice. Okay, so you do not know the perfect parameters. Like for example, the quantum computer send the parameters to the classical computer, and then the classical computer only chose the parameters twice, because you did not repeated the whole set of problem again and again. So the less the repetitions, the less will be the accuracy, and the less will be the precision of the particular finding the particular energy of a problem. So it is suggested that go for more repetitions to find the better value, so that you will get the better value, so that the parameters will be perfectly tuned, and you will get the better value. So why in running big molecules we use a lot of repetitions to find the ground state of a particular molecule. And also there is also some disadvantages with this, like to run the quantum phase estimation, especially for these molecular problems, it requires a huge amount of hardware. Like it requires a lot of qubits, because if you take hydrogen, there are only 2 electrons, right? But if you go for bigger molecules, as the number of electrons increases, it increases exponentially, right? It goes on 2 power n, right? Like so the number of electrons increases, then the number of qubits you need will gradually increase. It will at one point of time, for example, if you need to compute a particular protein, imagine, like, I mean, in a protein itself there are a lot of there are a lot of compounds in a particular protein, and each compound will have a particular chemical formula, like C2H5O2, like I'm just randomly telling. So again, you'll have a lot of electrons, and you need to find the electronic Hamiltonian, and doing all of this is a huge process. Like it is computationally expensive. So so the limitation for VQ is that it's not applicable for higher order electronic structure problems. Like it's limited only to like particular electrons. Like for example, it's only limited for you cannot go beyond 30. You can go, but the accuracy that you will be getting will be very, very low. So why it is suggested that so why wherever you see variational quantum eigensolver for H2 molecule, like they did not go beyond, like, I mean, they did go beyond, but for H2 molecule they found the accuracy to be very high, because it does not require a lot of qubits. So so the error rate will be decreased, and and also the present NISQ era, NISQ, noisy intermediate scalable quantum era, has a lot of errors in it. The error rate is very high, and also you need more number of qubits. So obviously the output is not precise. Obviously the output will not be accurate. So those are the advantages and disadvantages of the not disadvantages, the limitations of the current VQE. So once we have the particular like particular quantum hardware, then I guess like VQE is going to be useful in drug discovery. Like we can find new drugs for a particular set of what like for a particular set of disease. So once all we need is like a good quantum hardware. So we are proceeding in the right direction, I assume. Let me show you the Niskera's. So yeah. So in 2019, we only have 27 qubits. This is the the flowchart of IBM, like the Niskeros of IBM. So IBM has the map. It says that in 2019 it has only 27 qubits, but now we are in 2022. It has recently released a 433 qubit quantum computer, and then the roadmap. If you see the roadmap, like by 2026, it can go to 10K qubits. Right. So once you have a lot more number of qubits, then you can use like extend your the VQE to bigger problems. So now we are only using H2. We are only using to compute simple molecules. But once we have the 10K qubits, once you have the less noise and a good hardware, then you can go for higher molecules. You can simulate new drugs. You can compute new chemicals for discovering new medicines for a particular disease, right? So why we are interested in, we are very much interested, and there is a lot of hype going on for VQE in the chemistry industry, right? So it's not like we only depend on qubits. We should also see the error rates, see the time coherence, decoherence, and all of the other parameters. So yeah, let us go back to our previous slide. So yeah. So now let us discuss variational quantum algorithms. So variational quantum algorithms is like VQ is a like a type of a kind of variational quantum algorithm, I could say, because like it's mostly same like how variational quantum algorithms work is the same thing. Like it's the same how VQE also works. So variational quantum algorithms, as I discussed, like they have parameterized circuits. uh, like as other quantum algorithms, like they do not have parameterized circuits. Like you don't need to like change the parameters in those particular set of problems, like particular set of algorithms. For example, Shor, you can take Shor, or you can take HHL algorithm, as I discussed in the first slide. You don't need to have a parameterized quantum circuits for calculating the function, for calculating the value, right? So but in variational quantum algorithms, in finding the minimum value of a function, you need parameterized quantum circuits. Why you need parameterized quantum circuits? Because those parameters can be tuned, like those parameters can be adjusted. We need to adjust those parameters to find the lowest value of to find the minimum value of the function, right? So that is the main agenda we are working on. So we need the lowest value of a particular set of problem. So why we use parameterized quantum circuits? Parameterized quantum circuits is nothing but rotational gates, where you can like you can rotate, like for example RZ, RY, RX, all these gates. So you need to define the theta values so that like it's like machine learning actually. So you need to tune the parameters, and then you will get an output, and then you form a loop. So once you get the optimal result, like once you get the minimum result, okay, then you will be done with your processing. If you do not get your result, then you need to like you need to again send the results to quantum computer. Again, you need to change the parameters. You need to find the exact set of parameters, so that the output will be optimized, right? So that is how variational quantum algorithms work, and the flowchart says it all. Like for example, see the parameters. So in the circuit you have three things totally: ansatz and parameters. Like we will discuss what ansatz is in the coming slides, because it is the main thing. Like that is the main thing in variational quantum eigensolver. Choosing the good ansatz will like decrease a lot of your work, and it will also give you the best output. So let us discuss what ansatz is in the coming slides. But currently, like as we are discussing about variational quantum algorithms, as I have said, like it has parameterized circuits, like RZ, RY, and RX gates. So the parameters are being sent to the circuit. Like I mean, we form a circuit, for example, using those parameterized quantum gates. Like we form a circuit, and the circuit goes to the compiler, and then the compiler will like we execute the circuit, like the compiler will go to execution, and then it will execute the circuit and it will measure it, right? So where is the execution happening? It can either happen in the backend, or it can either happen in the real QPU, right? Like, I mean, the backend itself, like it can happen on the simulator, or it can happen on the real quantum hardware. So once you execute the circuit, you will measure it, right? Like if your measurement, then you will know whether your parameters are perfectly optimized or perfectly tuned or not. Once you After you measure like, you will compute the value, the cost value. So if that is not optimized, if that is not the lowest value that you could get, then you need to again go back, change the parameters, right? So that's how variational quantum algorithms work. So let us move ahead. So yeah, as I have discussed, the optimization loop, right? So these are all the parameters that you have in a variational quantum algorithm. So ansatz, Hamiltonian, constraints, and initialization methods. There are a lot of methods you can map the Hamiltonian to the qubits. So the choosing the methods can also be a parameter. Like, choosing the best method is really important. So all these parameters goes to the circuit preparation. So we prepare the circuit using all of these parameters, and then we execute the circuit, and then we compute the cost value. So the main agenda is the cost value should be the lowest value, right? Like, the cost should be very less. So if that is not the least value, then you go to the optimizer. The optimizer will again optimize these parameters, and again this loop goes on and on and on until and unless you find the lowest value for the cost, right? So how many parameters do we have? So we have total 4 parameters: ansatz, Hamiltonian, constraints, and initialization method. So are they constrained in any way? No, I mean, yes, like, I mean, they are constrained. Sorry, they are not constrained. Like, you can choose the parameters as you want for the first time. Like, while defining the parameters, like, you can choose your ansatz, right? Like, you are free to choose the ansatz, you are free to choose the initialization method, you are free to choose the Hamiltonian. So they are not constrained in any way. Like, once you send the parameters to the circuit, once it prepares and once it executes, and then your work is done, it will automatically optimize like, the classical computer will automatically optimize these parameters, and then it will give you the lowest cost value after a particular set of repetitions. So you need to be careful in choosing the repetitions. The higher the repetitions, the better the output, right? So let us move ahead to variational quantum eigensolver. So why do we care about VQE? As I discussed before, it is helping us to find the lowest eigenvalue of a given Hamiltonian. So to put it in layman terms, it helps us to find the ground state energy of a particular molecule, right? So I'm not discussing it in a to put it simply, I'm not discussing it in chemistry terms. Like, like, we are discussing it in layman terms to understand it better. So what I am telling here is not exactly how the same representation of VQE, but to make you understand how VQE works. So I am explaining it in layman terms. So let us answer these questions. Like, first, so what is upper bound? So let us take the example of a water well, right? So let us take a well. So what are all the bounds of a well? The upper bound of the well is the water, like, the level of the water. The Once the water comes out of the well, so that is not the upper bound, right? Like, the upper bound will be the highest level that a water can be in the well. So that will be the upper bound of a water well, right? The lower bound will be obviously the ground. The earth will be the lowest bound, right? So we need to be clear with these upper bounds and lower bounds terms, because VQE can help us find an upper bound of the lowest eigenvalue of the given Hamiltonian. So it can help us find the upper bound first, and then it can help us also find the lowest eigenvalue of the particular given Hamiltonian. So as I discussed now, so the limits of a water well is, upper bound will be the highest amount of water that can be in a well, like the highest level of water that can be in a well, and the lower bound will be the ground, right? So sometimes when we describe a physical system, it is hard to find the real value, but knowing the lower bound and upper bound can help us estimate what value it might be. Like, for example, if we know the upper bound and lower bound, then we know that the water can be in between upper bound and lower bound, right? Like, I mean, the water can obviously cannot go outside the well. So now we know the limits of a particular problem, so that we can be sure that the answer should be between these limits, and it should be it should be as near as to the lower bound, right? So because we are finding the lowest eigenvalue, so that so the output of the VQE should be nearest to the nearest to the lower bound. So now we know the limits, so that's how like that. So I just put it in the layman terms. So now we know the upper bound and the lower bound, so we should also be sure that the output that we get should be near to the lower bound. So next let us go to the Hamiltonian. So Hamiltonian is nothing but the matrix that describe the possible energies of a physical system. Uh, so let us, I mean, I'll show you, the Hamilton, how the Hamilton, as I discussed before in the previous slides, by Born-Oppenheimer approximation, we don't need to consider the other two terms, the interaction between electrons and the electrostatic interaction between electrons. So we can cut them off, and we are only left with three terms. So these three terms should be put in the, I mean, the language quantum computers can understand is qubits, right? So you should not, the Hamiltonian that we defined previously is chemistry, or the binary terms. So you should convert that Hamiltonian, you should map this Hamiltonian to the qubits. So that's how so that's how you tell the quantum computer, you go to the language of quantum computer, and you tell you define the problem to the quantum computer. So Hamiltonian is the central piece, like like defining the Hamiltonian is really important. It's a central piece of quantum mechanics. So let us proceed further. And so what is the eigenvalue? So as we discussed here, VQ allows us to find the upper bound. So I discussed what is upper bound and what is lower bound. So what is the eigenvalue? So it says that it is used to find the lowest eigenvalue of the given Hamiltonian. So each state, what is eigenvalue? So each physical system has different states, right? Like a physical system can be, for example, if you take a book, right? A book can be plane, a book can be horizontal, a book can be vertical, a book can be like, it has different states, it has various states. So eigenvalue is that particular a lowest eigenvalue corresponds to the ground state, or the lowest stable state. For example, uh, uh, like, how should I tell? For example, the book is at rest, right? Like, book is plain, so that will be the ground state energy of a book. So once you take it up, once you swirl it, once you like once you start like throwing the book, that is not the ground state energy of the book. So the ground state energy of the book is like, it should like it should lay at rest. So that is the ground state energy of the book, and the eigenvalue corresponding to that ground state energy is the lowest eigenvalue. So I hope I explained it well. Like, we once we go to the once we go to the code, then we can see the like eigenvalues and eigenvectors there. So just remember that the eigenvalue, the lowest eigenvalue represents the ground state energy. So instead of finding the ground state energy directly, once we found the lowest eigenvalue, it corresponds the same. Like, once we have the lowest energy value, the ground state energy that is related to the energy that is related to the lowest eigenvalue is the ground state energy of the molecule, right? So what is ground state energy? As I discussed, that is the lowest energy, which means the most natural state that a object can be, or that a molecule can be. So each molecule usually will be in ground state. Once you add energy, once you deduct energy, once you throw electrons to it, for example, hydrogen molecule, once you add an electron to it, the electrons get excited to another orbit, and then the energy, the ground state, I mean, the molecule will not be in ground state anymore. It will go to the excited state, or it will not be in ground state. So ground state is the most natural state that a molecule or that a object can be. Or like, to put it simply, if you leave it, it will stay there forever. For example, if you leave the book there, it will stay there forever, right? Like, I mean, until and unless you catch the book and take it somewhere, it's not going to change from that place. So that particular state is called ground state, or the lowest energy state. So I hope all these terms are clear: upper bound, Hamiltonian, eigenvalue, and ground state. So let us talk about the variational principle. So how is VQE working? VQE works using the help of variational principle. So what happens is like every problem can be defined in this particular like in the form of characteristic equation. So characteristic equation has eigenstates and associated eigenvalues. So what we need to find is like we need to find the lowest eigenvalue in through with the help of this characteristic equation, right? So we'll be lucky enough if the ground state energy is equal to the ground state, right? So we will compute this, right? So we will get a result. So if our ground state energy is equal to the actual state that we get, so for example, if our answer is x, if our ground state energy is also x, so both of them are equal, so we are good to go. Like, I mean, we found the real answer, like we got the answer and we are done. But if we don't get the ground state energy value, then again you need to send it back to the parameters. Like the parameters need to be adjusted with the help of, I mean, as I discussed in the variational quantum algorithms. So the parameters must be tuned again, and then you need to like solve the characteristic equation for h, and then again you need to compute the value, and then again you need to check the error rate or the difference between the real value and the like the computed value, right? So variational principle works on the characteristic equation. So yeah, so E5, so E5 should always be greater than E5. I mean E0, right? So it makes sense because E0 is the ground state energy. So whatever the value that you get should not be less than E5. That doesn't make sense at all, right? Like, I mean, telling that the lowest energy a molecule can be, let us think that the lowest energy a molecule can be is 1. So anything that you get should be greater than 1, right? Like only then it makes sense for us, or it should be either equal to 1 or it should be greater than 1. So once it is if you get the value that is less than the ground state energy, so you are doing mistake somewhere. I mean, it cannot be possible, right? Like how will we get a value that is not that doesn't make sense at all, because the ground state energy is the lowest energy that a molecule can be, or that a particular set of problem can be. So we should also make sure that the value that we are getting, once we compute this, the value that we are getting should be greater than or equal to the ground state. If we get the equal value, we are very lucky that we found the answer to our problem. If we don't get, if the value is greater than the ground state energy value, then we need to set the parameters, we need to tune the parameters. The process goes on and on. So that's how variational principle works. So it defines we have a particular problem, like to narrow it down. So we need to find the answer to this characteristic equation, and then we compute it, we check it with the ground state energy value. Once if the answer is equal to, then we found the answer, like we are done with our process. If we are not, like if the answer is greater than the ground state, then again you need to like set the parameters. You need to go to the classical computer, ask the computer to set the parameters for us, and then the classical computer will do the work for us. And then we take those parameters, and then we bring those parameters to our quantum circuit, and then we tune the parameters. We send a new circuit, then we compute that, we execute that in the backend, then we check the results again. So the same as variational quantum algorithms work, variational quantum eigensolver works the same. So let's go for ansatz. So what is ansatz? So the problem is that, like, we have a lot of space, as I said, like as I discussed before. So the lower limit and upper limit, right? So the possible states are so much. Like, how are we going to narrow it down? So the like how we work in VQ is like we cut off the unpossible things. Like, for example, we need to narrow down our problem so that we are working in a good space. Like, we are not working out of the space. So ansatz makes our things a lot simpler by like by decreasing the limits. Like, for example, the upper limit is 10 and the lower limit is -10, but our value is like the ground state energy is, let us think it is 1. So 1 -10 +10. So how much we have? So -10 to +10, there are 20 values, but the value, I mean, there is a lot of difference between 1, -10 and +10, right? Like, you need to check check minus 10, 10.1, 10.2, 10, sorry, plus 10, 9, 8, 7, 6, 5, 4, 3, 2, and then you will land up at 1. And from coming from the behind, minus 10, minus 9, minus 8, you need to decrease the value, and then you will land at 1. So what ansatz does is like it finds the best limits for our problem. So for example, the real answer is 1, or let us take it as 0. So ansatz make sure that the limits of our problem are for example 3 and minus 3, right? So now the search space got decreased, so it is not computationally expensive, right? Because the search space is decreased. Now you will now you don't need to repeat the algorithm so many times. Now you don't need to repeat it some 500,000 times to find the value. So once the search space decrease to the particular particular set of limits, so ansatz help us in finding that it explores all the spaces of all possible states in a reasonable manner using the parameterized quantum circuits. So as I said, the parameterized quantum circuits can be ry gates, rx gates, and rz gates. So these rz ry rz rotational gates can like has a rotational angle, and then you can change the angle. The classical computers will take care of that, and they'll tell you what are the exact angles that you need to put, so that you will get this value which will be equal to, which is not greater than e naught. So you will land in a particular value where the answer to this problem will be equal to, and it will not be greater than e naught. So I hope things are clear. So I hope what ansatz does is clear. So we use parameterized quantum circuits to prepare an ansatz. So finding a best ansatz is very necessary, because it narrows your limits down, so that your expensive, like it will not be computationally expensive. The time that you will find the right answer will be very less, because the search limit is not high. Before it was plus 10 and minus 10, now it got narrowed down to plus 3 and minus 3. So you don't need to search so many values. You don't need to knock the door of 10 and ask, oh, whether you are the correct value or not. You don't need to go to 9, 8, 7. So you don't need to ask so many values whether you are the right value or not. So you can narrow it down using ansatz, and then ansatz will help you in finding the best limits, in finding the best possible value. So that's how ansatz work, and ansatz are parameterized quantum circuits, which is to be noted. So finding the best ansatz covers many states. As I said here before, it will cover all the possible states, and it will narrow it down to plus 3 and minus 3. So we don't need to search elsewhere for our value. So it will cover all the possible values for us, and it will tell us, okay, you don't need to go there because the answer is not there. So you don't need to go there. So you only search between plus 3 and minus 3, you will get your answer. So it covers many states. Ansatz will cover many states, and the shallower the better, the less the gates the better. So the shallower the better, because the less the gates you use, the less the computationally expensive it is, and the less the noise, because we are in NISQ era, as I said before. So there is a lot of noise in quantum computers, in the backend, in the real hardware. So the less the number of gates that you use to compute, the less the more the shallower the circuit is, the better the ansatz. So how do you say that this is the best ansatz? So these are all the parameters. So the best ansatz should cover as many possible states as it could, and tell us the least possible states. And then it should not be it should not be with so many gates or so many. It should use it should find the best possible circuit for us, so that it will be it will not be computationally expensive, and it will be shallower, and it does not have too many parameters, so that if you have too many parameters, so you need to repeat the process. You need to repeat this loop. uh, yeah yeah, you need to repeat this loop again and again if you have too many parameters. So the best ansatz should not have too many parameters, should only have the exact number of parameters that are required for solving the particular problem. So the best ansatz covers all of these. So choosing the best ansatz, so we choose the best ansatz like this. So we check whether the ansatz is covering so many states or not, and we check whether the ansatz has less qubits, or whether the ansatz has a particular set of gates. For example, if you are using X gate, and if it is not necessary, so the ansatz should be chosen such that the Qiskit is not there. Then, so because we are not using Qiskit for anything, and if the Qiskit is already there, it's computationally expensive, and it will increase. It's unnecessary basically. So choosing the best ansatz is important. So how do we choose? Are basically these three parameters. So let's go ahead and let's see how VQE works. As we discussed in the first slide, we said that it's hybrid quantum classical algorithm. So why did we say it's hybrid? Because it brings classical optimizer into picture. Whereas in other algorithms like Shor algorithm, HHL algorithm, and other only quantum algorithms, we don't need a classical optimizer to do this. So we just compute the result, and we don't need classical optimizer in other algorithm. So why we call it a hybrid approach? Because we use both quantum as well as classical optimizers in this problem. So what QPU does is, QPU is only used to get the energy value for a given. I mean, we give the parameters to it, and it will compute. So this is the QPU. Like we work. I mean, this is the parameterized quantum circuit. And then this is then you measure that, right? Like, and then you will get the output. That is, and then you send this output to the classical optimizer, and then you check whether the E naught, like E theta, is equal to E naught. Like E naught is the ground state energy. So if E theta is equal to the E naught, then we are done with our answer. Like we found our answer, right? So if this E theta is greater than E naught, which states that the lowest outstate energy, I mean the energy that you found is greater than the energy of ground state, then you go to the classical optimizer. You repeat until the convergence is obtained, like the minimum value, like these thetas, which can be changed here, like in the parameterized quantum circuit. And then you get a new set of theta values. The classical optimizer will give you a new set of theta values, and then you put those theta values, and then you compute the problem again, and then you will get a new E naught this time, sorry, new theta value this time, and you again check whether the new E theta value is equal to the ground state. So once the new E theta value is equal to the ground state, you stop the process. You cut this off. Like, you don't need to go to the classical optimizer and ask the classical optimizer whether you are the real ground state or not. So I hope how you are clear with how VQ is working, how why we call it hybrid quantum classical algorithm, or I hope you are clear with the hybrid approach. So I'll just repeat this again, because this is the basic, what's happening behind VQE. So I'll just brief it out again. So you will have we will prepare a parameterized quantum circuit, and we'll have an ansatz, and we measure everything on QPU. So QPU is only necessary for measuring the energy value. So QPU does not do anything else. Like, it just measures. You give the quantum circuit, and it will measure the output for you. So everything else is done by CPU. So the measured output will be checked with the ground state value. If the measured output is equal to the ground state value, you does not do the process. You don't need to go to the classical optimizer and ask the classical optimizer to set the new parameters, like change the new values and bring the new theta values for us. If the output of the QPU is greater than the lowest ground state energy, or the ground state energy of the molecule, then you need to go to the classical optimizer, and then you need to ask the classical optimizer to converge to find the minimum values for this theta. And then you put the new theta values in the you put the new theta values, you give the new theta values to the QPU, and then it will compute it again, and then you repeat the process, as I have mentioned before in the previous slides. Okay. So as I have also mentioned before, like I said that we are in the NISQ era, noisy intermediate scale quantum era. So let us see what are the disadvantages. We know the advantages. Advantages, like we can use it is a lot better than having nothing, right? We are in the noisy intermediate scale era, but at least we have some noise, and we also have we have disadvantages. Like, we have a lot of noise, decoherence, like qubits won't live for a long time. As I have also mentioned that the number of qubits are very low, like 433. Like once you 2 power I guess 2 power 19 or 20 will come around 433, right? So 433 is nothing. So you need to have at least 10K to compute if you want to compute bigger problems. So there are advantages as well. At least you can now have a quantum computer, and you can now solve some. You can check the ground state energies of at least some low molecules like hydrogen, helium, lithium, something like this. But that is not enough, right? Like we already know, like we are not interested in low molecules. Like we want to find drugs, new chemical formulas, new chemical materials, all of that. We are interested in that. Like we already know how hydrogen, helium, lithium, all of these lower order elements work. Now we are interested in bigger problems, but because of the noise and because of the less number of qubits, we cannot extend our problems there. Like we are not at here. Like, but IBM, the roadmap says that by 2026 we'll have 10K qubits. And once we have the good quantum hardware, then we can extend our VQE to compute bigger chemistry problems like drug discovery, like how proteins fold and all of that. So so as I discussed before, the disadvantage of NISQ is it has a lot of noise, and the qubits won't live for a long time, which is decoherence. And then the number of qubits are very low, as I showed in this slide. It's only 433. We at least need some, like more than 5,000. It should be in thousands at least, like to compute some bigger problems. So why is VQE sensible for Niskera? So why are we like I said that like we all have a lot of disadvantages, but why are we using VQE even though we have a lot of noise? Because VQE is somewhat resistant to noise, like where compared to other algorithms like VQE, like QPE, quantum phase estimation, and VQE is somewhat resistant to noise. Like it does not take complete noise into consideration. It works fine with noise. Even the quantum computer has noise, it works fine with noise. So practical problems that do not require a lot of noise, for example, like if you want to compute a practical problem, then like you don't need to consider noise into consideration. So like VQE works only on practical problems. Like for example, finding H2 is a practical problem, right? Right. So finding the ground state of H2 is a practical problem. Like in the next slide, I'll also discuss the practical application of VQE. So noise, we can exclude noise for VQE. So I mean, not completely exclude, but at least it's not compared to other algorithms. It does not take. It is a somewhat resistant to noise at least. So VQ is also flexible with circuit depth. So why we are using VQE to in Niskera. So there is this practical application. There is this paper called titled "Variational Quantum Algorithms for Chemical Simulation and Drug Discovery." This work is done at Fractal Analytics, India. So I'm also one of the I'm also one of the author to this paper, and other volunteer called Srinjoy Ganguly. Even he's also he's also author of this paper. So what we did here is like we used variational quantum Eigensolver and quantum QAOA, quantum approximation and optimization algorithm, to find the ground state energies of particular set of protein. We did not take complete protein into picture. As I have said before, we do not have a lot of qubits. We only have 433 qubits. So I did not take sorry, we did not consider the whole protein into consideration. We just took the main chain or the small peptide of a protein. So each protein has a lot of peptides. So only we took one peptide, and in that one peptide we only took the main chain. We also took the side chain for other computations, but this is the main the result we got. So VQE, the ground state is 391.16. We also used error mitigation techniques. So you can see the difference between ground state energy and the error mitigated once we use the error mitigation techniques, then the ground state energy is even more less. So it says that error mitigation energy, like error mitigated technique worked here. So we found the lowest energy value. I mean, I'm not telling that this is the lowest, but when we computed this on IBM Perth, when we computed this on IBM Perth, the lowest value is found to be 86.89. But we use CVAR VQE, conditional value at risk VQE, then the ground state is found to be minus 1.019. And we took this as the standard, like because this is the lowest value we got when we found the results, when we computed when we computed this particular chain onto quantum computers and found the ground state energy. So we thought, I mean, we consider minus 1.019 as the ground state energy. So how did this work? So what are we trying to find here? What are we trying to find here is like yp by fip is a particular like each peptide, like yp by fip. So what are we trying to do is like we are trying to find the ground state structure of this particular peptide, okay, the particular protein structure using vqe. So what we did is like this is our computed value, like this is the structure that we got with the help of vqe, like using this energy, like minus 1.019, sorry, using this 86.89 or 319.16. And then we plotted the molecules onto the graph and we connected them, and then we compared our results with AlphaFold. As you can see, QAOA is like this one, like the YPYFIP in yellow color, and the red one is AlphaFold. You can see there is a lot of vast difference between quantum approximation optimization algorithm, the result of quantum approximation optimization algorithm, and the AlphaFold, right? So so this tells how much we need to improve in the field of increasing the number of qubits, right? So you can see by yourself that AlphaFold has done a better job than quantum algorithm, like than VQE or QAOA. So so we conclude that through this research paper, we conclude that like the quantum like to find, for example, to use this for chemical simulation and drug discovery. If you want to use variational quantum algorithms for chemical simulation and drug discovery, we need a lot of qubits. Like the current number of qubits are not enough for like to compute this. But AlphaFold, using classical techniques, using classical machine learning, like AI techniques, deep learning techniques, they found the answer to be this. But when we compared that with our quantum result, it's nowhere comparable. So we conclude that we need a lot more lot more qubits to if we want to work on practical applications like this. We need a lot more number of qubits. So that's it, guys, for today. Like, I mean, if you have any more doubts, like please. Oh, sorry, I forgot. Like I thought of sorry, there is a code version. Like I'll just briefly like show you how it works. Like as I said before, it's the same. Like there will be classical optimizer. You need to prepare an ansatz. Hamiltonian, you need to do it, and it will give you the energy. So then you will find the lowest energy. So as you can see, the lowest energy is minus 1.11, which is the real value which is found out. So I'll just briefly explain how VQ works, and I'll also take you to IBM's. I'll also like run this and show you how like show the main motivation for this. Practical application, our main motivation, from where we got motivated to work on this project. So this is quantum protein folding algorithms by by IBM, actually. So actually I thought of explaining you the same thing, like the how to compute a protein on using VQE through Qiskit. But actually what they did is like they removed the code from one particular place to they added a new GitHub called quantum IBM research, which is not installable, like which has problems. And also it is recently they did it recently. Before it is in IBM nature, Qiskit nature. Now they did it, now they moved that from Qiskit nature to Qiskit research. So I'm not able to install the pip install. Qiskit nature is not installable yet, and like I cannot also clone the repository. But if you are interested, I can send you the link to that, and you can use that to find the find the molecules, like find the the ground state structures of proteins. So this is particular protein, like they said that they used the algorithm, they used a particular protein. I guess they used Alzheimer disease protein, like the protein that causes Alzheimer disease. So what we need to find here is, like, this is the random structure. So we need to find the ground state energy of this protein. So the ground state energy is the state, as I have mentioned before, which will have the lowest energy, right? So this is the energy versus generation graph. So we need to find the lowest energy. So let us fold this angiotensin peptide. This is the angiotensin peptide. So let us fold this and see the ground state energy for ourselves. So it will take some time. You can see that the energy value is slowly decreasing as the number of iterations are increasing. So 10, it got decreased, and 20, it will slowly decrease, and uh, it will optimize itself to a ground state. So it's tetrahedral lattice. Like, I mean, first you will YPY FIP. If you take YPY FIP, first you will have Y, and then you will have YPY. Then the P can be placed at 4 different places, and then you will compute the distance, and then you will find which distance is less, and it works like that. Like, it's tetrahedral lattice, which means you will have 4 different places a particular problem can be. So you can see that this is the ground state energy. So this is the stable structure of the protein, right? So this is the stable structure of the protein, and the energy, you can see, actually it started from 2644.3. Hadry Fock can also be the unit of energy, but they use some other thing. So it slowly got decreased. It got decreased the second iteration, third, fourth, fifth, sixth, and the stable structure, as you can see, it went to minus 2.1, right? So that's how, I mean, there is back end work. There is also the back end work on how it is working. Like, I'll give you the code for that. Like, I'll drop the code and the IPYNB Jupyter notebook file for that also. If you are interested, you can also read the paper here. Like, this paper is the main motivation for this for this paper, like for variational quantum algorithm for chemical simulation and drug discovery. If you are interested, you can also go through this paper. Our team has worked very well, and like, we compared our results with also AlphaFold. So yeah, like, so that is how IBM, like, IBM research, they are working on quantum chemistry and variational quantum eigensolver. They are using VQE to find the ground state energies of proteins, and like, the stable structure of proteins, because protein folding problem is, in biochemistry and biomedical fields, protein folding problem is one of the biggest problem. Like, they are like, we never know how proteins are like, folding. Like, we like, it's like a hair. Like, if you take your hair, and then if you leave it, it folds in different ways. Like, but obviously it will go to the ground state. So we know that it is going to the ground state, and once you have the ground state, so we are sure that that folding is the particular folding that a protein will go when you leave it. Like, when you just leave it, the protein will fold in such a way that it will the final energy of that particular folded protein will be the ground state energy. So you can also compute neuropeptide. This is angiotensin peptide, and this is neuropeptide. So you can just fold it, and you can check it for yourselves. I'm not going into that part, but if you are interested, I'll also draw. You can read the paper, and I'll drop this link to you. So let us go to variational quantum eigensolver and how it works. So this is the unitary matrix. As I have said, that Hamiltonians are nothing but like, we can compute it using matrices. So like, we once, for example, what we need to find here is, like, we need to find the like, stable. For example, we need to find the structure of ground state energy of this thing, like I1, I2, Z1, Z2. So what we do is, like, we need to compute that. We need to find a final matrix for that. For example, I1, I2 plus Z1, Z2, we will, so Z1 tensor Z2. I hope tensor products are clear to you. In the first lecture or second lecture, I hope our volunteer has covered that. So we compute the tensor product, and we bring out the matrix that will be used as a Hamiltonian. And then like, we measure it. Like, we change the basis. So for example, HZH. So we take that, and we compute the Hamiltonian. Like, and once the parameters are ready, we send it back to the quantum simulator, as I have discussed with this thing. Sorry. Yeah, so once they are ready, we execute it in the backend. And so this red color, one we execute it in the backend, which is we execute it in the Cosm simulator backend, and then you will have then you will measure it. Yeah, then you will measure it, and once you have the measurement, and then you check for yourselves whether the answer, I mean, not for yourself, like you return the energy, you return the energy to the classical, like the classical part, and then the classical part will tell you whether that is the lowest energy or not. And then you, like for theta equal to 0.2, the energy you got is 0.98. Our aim is to find the value of parameter that is the lowest possible energy, and that is decide. So we found out that for theta equal to 0.2, so we got 0.98, which is the lowest energy value that you could get. So that's how VQE works. So you can see here that energy is 0.980713. So how do you find this theta? You find this theta using classical optimizer. uh, so I'll also share this wiki code with you, and I'll also share some of the links that you could, like you can check for yourselves. You can read some of the blogs and all of that to you in the Discord. And yeah, like that's it for today, guys. If you have any doubts, please go ahead. Like I would be very happy to answer.
No doubt, sir. It's clear.
Okay, so yeah, I'm stopping the recording then.